Hello everybody. In this video, we're going to learn about double integrals. Double integrals are kind of like integrals you learned back in single variable calculus, except there's two of them. Also, there's multiple variables, and very interestingly, they let you calculate the volume underneath a surface. So there's a very close analogy to what you learned in Calculus 1 or Calculus 2 in your single variable calculus class. You might remember learning about the area under a curve. But let's review where the theoretical foundation comes from. To begin, you approximate the area under a curve, say y equals f of x, by creating a set of rectangles. So here, I've got a total of 5 rectangles, and each rectangle has the same width along the x-axis. That's called delta x. So every rectangle has width delta x. To calculate the height of each rectangle, I take these equally spaced points along the x-axis and plug them into the function f of x to get the height of each rectangle. So the height is f of x sub I, where in this case I ranges from 1 to 5. So then we sum up the area of each of these rectangles, multiplying the height times the width, and that gives us an approximation to the true area under the curve between these two values. I'll call them A on the left and B on the right. To improve the approximation, you use more rectangles. And then we're brought to the idea of limits once again, limits which are useful in calculating derivatives and slopes. They're also useful in calculating integrals and areas. And so we take the limit as n, the number of rectangles, approaches infinity, and then that defines the definite integral. And then you've probably also learned about something called the fundamental theorem of calculus that says you can solve this kind of question using antiderivatives, which is pretty amazing. Now in multivariable calculus, as we briefly mentioned before, we're going to be calculating the volume under a surface. So let's say this mountain shape is a graph of the surface of the multivariable function z equals f of xy. To calculate the volume underneath a surface, we'll approximate it as the sum of the volume of a series of boxes. The volume of each individual box can be calculated as the height of the box times the width of the box times the depth of the box. So just as in Calculus 1, or maybe Calculus 2, when you're calculating the area under a curve, right, you divide the x-axis into line segments. In multivariable mathematics, you'll be finding the area under this surface that lies above some kind of a rectangular region. And you'll divide that rectangular region into a set of, well, little rectangles. Right? You'll partition the x-axis, but also partition the y-axis. And each pair of xy values will give you a point to plug into the function, and at that point it'll give you the height of the box. So in this case, I'm looking for, in this example, the volume under this surface, but lying above this grid of 12 boxes. In this case, I'll use the x values x1, x2, and x3. And so the x sub i's will range from 1 to 3, but there's a second summation. For each of those values of x, we must also consider these values of y. So the y values are y1, y2, y3, y4, y5. Really, we only need one corner of each box. So in this case, the y values, I need to use a different subscript for y, so I'll say y sub j. The j values range from 1 to 4. And so this double sum for each of these values of j, we'll use each of these values of I. So there's 4 times 3 boxes altogether. The height is the value of the function at each one of these points. The width is the space between the x values. We'll say the depth is the space between the y values. We'll call those delta x and delta y. Now the idea is, what worked for single variable calculus works for multivariable calculus. We just have to do it twice. So we'll have two limits of two summation notations. Now some of these terms can be rearranged. In particular, I'll take the limit as m goes to infinity. I'll kind of factor that through to the inside. The value of m does not affect this first summation. So we'll move this limit inside here, right? And as the value of I changes, right, these points x sub I are changing, but the value of y sub j is determined by this outer summation, right? So when calculating this inner summation, it's like the x sub I varies and the y sub j is held constant for each value of j. And so we'll kind of group those together. And hopefully that sounds maybe a little bit familiar, like what we did for partial derivatives. The same kind of ideas come into play when calculating double integrals, as we will soon see. And so now, taking the limit on the inside here, right, within the set of parentheses, that's really the definition of the integral. And then it's as if we'll take this function, right, this integral, if we integrate with respect to x, we will be plugging in the values a and b for x, but we'll still be left with a variable y. So what's within these parentheses will turn out to be a function of y, which we can then integrate again. And so we'll have some boundaries, a function of y, and then do an integral with respect to y. Again, these letters a, b, c, and d, they assume that they're the bounds. The bounds of the x values are between a and b. The bounds of the y values are between c and d. Right, so the double Riemann sum just leads us to a double integral. And this will give us the exact volume underneath this surface, but lying above this rectangular region in the xy plane. However, there's an asterisk on volume here. By volume, I actually mean signed volume. Right? Just as is the case in single variable calculus, right, this function could in fact be negative, which will give you a negative contribution to the volume. And so in this case, the signed volume means boxes that appear above the xy plane have a positive volume. Boxes whose height is negative, they'll appear below the xy plane. We'll consider them as negative. Right, so when we say volume, we really truly mean signed volume. All right, and that being said, let's just jump right in and calculate a double integral. And so we'll assume that you know the antiderivative rules. Mostly we're just going to be working with polynomials, so you'll need the power rule, and we'll sometimes work with sine and cosine as well. So it will help to remember those antiderivatives. So let's say we want to calculate the volume underneath probably my favorite multivariable function, z equals f of xy equals x squared times y cubed. So the volume underneath this surface, but above the rectangle, where x ranges from 1 to 3 and y ranges from 1 to 2. Right, to set this up, in this case, I'll put dx on the inside. And you can put either dx on the inside or dy on the inside, right? We'll learn how to do both over the course of this lesson. For now, dx is on the inside. It's very important that the bounds on this inner integral correspond to the variable, which is more to the inside. So since dx is in here, I'm using the x bounds from 1 to 3 on this integral. Now, we have to respect the order of operations no matter what we're doing. So this inner integral, we must calculate this first. Now, within this integral, the dx indicates that x is being treated as a variable, and we should think of y as a constant. This is very similar to what we did with partial derivatives. Right? So here, we're integrating the function of x squared times a constant. Right? The antiderivative of x squared times a constant, well, by the constant multiplier rule, it's x cubed over 3 times that constant. Right? So for this inner integral, this antiderivative is going to be 1/3 x cubed times this constant y cubed, and then we need to evaluate it between these bounds. And I'm still using this line notation, meaning to evaluate this expression. Right? And I also, just to be very clear, to reduce the possibility of a mistake, I'm saying x equals 3 and x equals 1. And for these numbers, to make sure we remember to plug them in for the correct variable. We plug in the top value first, and then subtract, plugging in the bottom value. So first plug in 3 for x, and we'll get 27 over 3 times y cubed, minus, plug in 1 for x, we'll get 1/3 y cubed. When you subtract, you get 26 over 3 times y cubed. Right? The result of this inner integral is a function of this variable. In this case, it's a function of y. And now, well, we have to integrate that function. Right? This part in purple becomes 26 over 3 y cubed. And now this becomes a single variable calculus problem. Right? There's just one variable left. So we want to integrate this. According to the power rule, we add 1 to the exponent, we divide by the new exponent. So the antiderivative is 26 over 12 y to the 4th. We need to evaluate this from y equals 2 to y equals 1. So first plug in 2, and also reduce the fraction while we're at it. So 26 over 12, we can cancel out a factor of 2, leaving us with 13 over 6. 2 to the 4th power is 16, minus 13 over 6 times 1 to the 4th power, which is 1. Right, doing the math, we'll end up with 195 over 6, which reduces to 65 over 2. And fortunately, for this kind of problem, there's actually a built-in check. There's not always, but when there is, it helps to make use of it. We can actually calculate this in the opposite order. Right, so first we integrated the function, we did the x integration first, and then the y integration second. But we can reverse the order of both the integral bounds as well as the variables of integration. Right, so we'll rewrite the problem in this form. Right, so as always, we always integrate the inner expression first, respect the order of operations and those parentheses. So here, dy indicates that y is a variable and x is a constant. And so this inner expression is a constant times y cubed. While the antiderivative is the constant times y to the 4th over 4. And we need to evaluate that at the bounds from y equals 2 to y equals 1. And so we plug in 2 for y. We'll get x squared times 16 over 4. Minus, plug in 1 for y. We'll get x squared minus 1 over 4. And subtract, we'll get 15/4 x squared. Right? If you integrate y first, the result will be a function of x. Once we have this function, well, it becomes a single variable problem. We're integrating the function 15/4 x squared between 1 and 3. Well, here, the antiderivative, we add 1 to the exponent, divide by our new exponent. The antiderivative is 15/12 x cubed. We'll evaluate that from x equals 3 to x equals 1. In this case, 15 over 12 also reduces to 5 over 4, so we'll simplify that at the same time. Plug in x equals 3, we'll get 5/4 times 27, minus, plug in x equals 1, get 5/4 minus 1. So that becomes 5 times 26 over 4. Do a little bit of cancellation, and once again, we get 65 over 2. So whichever way you look at it, the x first or the y first, you're going to get the same volume. All right, let's do another example, this time with a slightly longer function. let's find the volume under this surface. I don't know why I wrote a plane. This isn't a plane, this is a surface. Z equals f of xy, which is equal to the function 2x plus 3y plus 12xy. I'd like to find the volume, the assigned volume, under this surface, but over the rectangle, bounded by x goes from 1 to 5, and y goes from 2 to 3. We'll integrate with respect to y first, so dy on the inside, which means this inner integral, the bounds should be the y bounds, so 2 to 3. Then we have to integrate each of these terms with respect to y. Y is the variable, we need to treat x as a constant. Again, the same mindset you use when calculating partial derivatives. Right, so the integral of a constant with respect to y is that constant times y, so 2xy. The antiderivative of 3y is going to be, see, by the power rule, we add 1 to the exponent, divide by the new exponent. So that becomes 3/2 times y squared. And here we have a constant times y. Right, so the antiderivative is going to be that constant times y squared over 2. But dividing by 2, we can simplify that with a 12. We have 6xy squared. So there's our antiderivative. We will evaluate it from y equals 3 to y equals 2. So plug in 3, subtract, plugging in 2, and then once you simplify, you'll get 32x plus 15 over 2. And that's the result of simplifying the inner integral. The result, as usual, is a function of the outer variable, in this case a function of x. And so here we have the integral from 1 to 5 of 32x plus 15 over 2 dx. Well, let's use that power rule once again. The antiderivative is 16x squared plus 15 over 2 times x. We need to evaluate that between x equals 5 and x equals 1. So plug in the 5, subtract, plug in the 1, and then when you simplify that, you get 414. That's all there is to it. It's, again, hopefully some of your single variable calculus is coming back. It's a combination of the antiderivatives combined with thinking in partial derivatives, right? Holding one of the letters as a variable and holding the other as a constant. I'm a big fan of You Learn Math by Doing Math, so what I'd like you to do is check the answer in that previous example. Right, in this example, we integrated with respect to y first and then x second. So I'd like you to switch these bounds, switch dy and dx, and then integrate it and see what you get. And if I didn't make any arithmetic mistakes, I'm hoping you get 414. Right, so here's the integral in its other setup. In this case, integrating x first, right, so the x bounds have moved to the inside, and integrating with respect to y second, so the y bounds are on the outside. So go ahead and integrate this part first. Treat x as a variable and y as a constant. Right, so then you'll get the antiderivative. You'll plug these values in for x, and you should get a function of y. Then integrate that function of y and see what you get. And that's double integrals. That's how you calculate the volume under a surface. Now there are a couple other variations on double integrals that you can do, and we'll do those in the next 2 lessons. First, you might be wondering about what if the bottom area is not a rectangle? We'll learn how to do that. In particular, circular boundaries are very tricky, so we'll learn about that in 2 videos from now. But this is a good breaking point for now, a good introduction to double integrals. Thanks for watching.